Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Hi, welcome to the MIT Faculty Forum Alumni Edition. I'm Wade Roush, Outreach Officer for the Program in Science, Technology, and Society at MIT and fellow MIT alum. And I'd like to welcome you to today's talk. We're going to be focusing today on music and the brain, and we've got alumni joining us from Mount Holyoke College here in Massachusetts, from the College of New Jersey in New Jersey, and from NYU. I'm going to let them introduce themselves and talk about their research. But I wanted to let you know that you can ask questions that I will relay to our alumni guests today, and you can do that just by using the form underneath your screen there in Google Hangouts. Those questions will show up on my screen, and I can pass them along to the guests. If you want to tweet during the session and let people know what's going on, you can use the hashtag MITalum, and we'll get to as many of your questions as we can. So this whole area of music in the brain, I think, is one that is on people's brains, not only because this is sort of an era of relentless self-improvement and everyone wants to know whether being a musician or listening to music can keep their brain young and supple. But I also think that we're obviously learning a lot thanks to various kinds of brain measurements and monitoring technologies about the connection between music and other forms of cognition like language and what's going on inside our brains when we're thinking musically. So our guests today are all in interesting positions to be able to talk about that, and have all been looking at those questions since they were here at MIT. So what I'm going to do first is introduce Breen, who's an assistant professor of psychology and education at Mount Holyoke College. And Mara, why don't you tell us a little bit about your current research and, if you can, how it connects back to your PhD work here at MIT.
Absolutely. Thank you so much, Wade, for having me. So I got my PhD in 2007 in Course 9, Brain and Cognitive Sciences, and I worked in a language lab with Ted Gibson, who's still there now. And so as a cognitive psychologist, while I was there and even now, I'm really interested in questions about language and music, the intersection between those two things. And as a cognitive psychologist, I'm particularly interested in what cognitive processes underlie language and musical processing. So, for example, attention and memory and imagery. And so in my lab, we conduct behavioral experiments, so reaction time experiments or things like that. And then also I have an electrophysiology lab, so we hook electrodes up to people's scalps and we record their brain activity while they're engaged in various language and music tasks. So I'm specifically interested in prosody, which I describe as the music of language, and in fact that was also the focus of my doctoral work at MIT. And so when we talk about prosody, we're talking about the musical aspects of language. And so that means things like intonation, so the difference between a rise at the end of a sentence versus a fall, right, which might be the signal the difference between a question and a statement. We're also interested in questions of phrasing, so how do people impart disjuncture to the things that they're saying, right? What do phrase boundaries indicate to listeners? And then also things like stress, so where do people put the stresses or the accents on words or syllables? And then finally, the focus of my research recently has really been on speech rhythm. So one of the challenges that we have as language users is that language is quite ambiguous. So everything that we're hearing in real time can be many different things, and we have to use context to kind of figure out what a speaker intends. And so I'm really interested in how rhythmic context can help us understand what we're hearing. So in collaborative work that I did with Laura Dilley, who's actually also an MIT alum, who's currently at Michigan State University, we were interested in how listeners can use rhythm to resolve ambiguity in spoken language. And so we had sequences like timer derby, which could be divided up into timer derby or tie murder bee, right? So it's ambiguous in that way. And we showed that the rhythmic context in which those phrases occurred could actually influence how people segmented that ambiguous string of syllables into words. And so if you put those in a in a context, I'm going to sing for you right now, like banker, helpful, time, murder, bee, people were more likely to report that they heard time, murder, bee. Whereas if they heard banker, helpful, timer, derby, they're more likely to report timer, derby. So in both cases, the 4 syllables themselves are acoustically identical. It's just the context that changes. But we show that that rhythmic context influences how people understand it. And then we took it the next step to say, well, again, what are the cognitive processes that might be underlying this effect? And so we put electrodes on people's heads, recorded their brain activity while they were listening to sequences like that, and we showed that this marker of attention, of temporal attention, so where you kind of allot the focus of your attention in time, followed the stress syllables. So that is, when you heard a context that induced you to hear stress on a particular syllable, you also allotted attention to those syllables. And this makes sense as kind of a general good idea in language processing to allot attention to the first syllables of words, because those syllables give you much more information about what you're hearing. And then also in English, because the vast majority of our 2-syllable words have stress on the first syllable, it's a good idea as a listener to adopt this strategy of allotting attention to those stress syllables. So that's one piece of what I've been doing. And then in another collaboration that's a little bit more focused on song, we've been looking at Diana Deutsch's speech-to-song phenomenon. And so many people are probably familiar with, she has this phrase, sometimes behave so strangely. And when you hear it repeated over and over, it starts to sound like she's singing. And so with some collaborators at Tufts and at Birkbeck Institute in London, we've been looking at what are the characteristics that might lead a particular utterance to transform into singing. And it looks like one of the predictive factors is to what extent the pitches in that utterance actually sound like songs. So to what extent could they come out of a song and outline a particular musical key. So that's some of the work that I've been doing these days.
There's a terrific Radiolab episode, I think, where they use the sometimes behave so strangely and really make it real music.
That's right.
Okay, listeners, your homework is to go out and listen to that episode of Radiolab.
It's a good one.
Sometimes behave so strangely. Yeah,
exactly.
It's stuck in my head. So just a quick follow-up, Mara. So do you feel like you're systematizing maybe insights that have been obvious to lyricists and songwriters for centuries, maybe without actually knowing how to put it in code or in words? The things you say about linking musical context with syllables, for example, seems like that's exactly what a good songwriter does, right?
I think you're absolutely right. And so one of the things that's really interesting is cases where we hear music where the stress and the strong beats like don't line up. So, you know, Taylor Swift's song, sorry, I'm not up on my Taylor Swift, where she says, all the Starbucks lovers, right? Help me out here. It's her, blank slate, right? And so she says, all my ex-lovers, but it sounds like Starbucks lovers because of where the stress falls, right? So I think I, for one, like really attend into those cases where there is kind of where the lyrics don't kind of match up to where I think the thing should be, right?
Yeah.
And in fact, somewhat paradoxically, often in those cases, they kind of grab your attention even more, right? So I think that's one of the powerful thing about cases where the beats don't line up exactly where we think they are. That's kind of like jarring, and we actually kind of perceive it as more interesting. So I think you're right, yeah.
Okay, thanks for tolerating my silly question. So, okay, so
at all.
We're going to keep things moving, and I'm going to introduce our next guest, who is Teresa Marrin Nakra, who got her master's degree in 1996 and her PhD in 2000 here at MIT, and she's now associate professor of music at the College of New Jersey. So, Teresa, why don't you explain a little bit about what you're up to now and how it relates back to your work at the Media Lab?
Great, Wade. Thank you so much. What a pleasure to be able to participate in this webcast. It's really cool. So gosh, it's been 15 years since I finished my doctorate, and so many great memories from MIT. One of the things I'll do is share some pictures in a minute. But so I got the chance to work with Todd Mackover and Roz Picard at the MIT Media Lab, and had an opportunity to work on a project called the Breen Opera, which was an attempt to bring ideas from artificial intelligence into the applied world of music performance, and got to perform it over 150 times on 4 continents while I was a student. It was an incredible experience and one that I'll never forget. After working on the Breen Opera, I got the chance to collaborate with the Boston Pops Orchestra and Keith Lockhart. He invited us to design a conductor's jacket for him. We came to him with some ideas about physiology monitoring of conductors while they conduct and while they perform and rehearse. And so got to work with him in a live concert in Symphony Hall in front of 2,300 MIT alums. It was quite a stressful experience, but also an amazing one. And the results of that are in the permanent collection of the MIT Museum. It's really a project I'm very, very proud of. And since MIT, I've moved out into the world of applied in a way, brain research, looking at applications in music performance, music education, and a range of interactive applications for museums. So let me pull up a couple of images. So since that sounds very abstract, you might wonder exactly what I'm talking about. So let's see if I can pull up, share my screen here. Can you see that? So there are the professors that I got a chance to work with during my time at MIT, people who influenced my thinking. On the bottom right, you see Marvin Minsky, whose office was a couple doors down from me when I was working at the Media Lab. And I just remember many, many late-night conversations about cognition and music held at the disclavier piano in the common room at the Media Lab. So just lovely time. And here, one of the stories that came out of the Conductor's Jacket project was really the close mentoring that I received at MIT. It's one of the things I think is very, very special about the Institute. You see there in these pictures here, Roz Picard is talking to me about things that maybe we needed to resolve as we were leading up to that live concert. And so sometimes successful outcome comes from, deep collaboration and conversation with a mentor, and some of those experiences were really, really meaningful to me. In the upper left-hand corner, you see the digital baton that I invented, and there's some examples of the conductor's jacket in various places. And beyond MIT, here are some of the applications I've built. In the upper left was a wearable sleeve for conducting students at Arizona State University. They got to practice their conducting assignments and etudes in a room with a computer, watching their movements and telling them whether they were conducting correctly or not. In the upper right is an example of a application of a performance with the BBC Scottish Symphony, where we put sensors on the arms of the conductor while he conducted in a live concert. And in the bottom left and right images are interactive systems that have gone around the world. On the left is the You're the Conductor exhibit that started at the Boston Children's Museum and moved off to children's museums around the country. And on the right is an example of the UBS Virtual Maestro, which sat in concert hall lobbies all over the world for a couple of years. Several years ago, it used a Nintendo Wiimote as a conductor's baton. So there are some examples of the kinds of things. So clearly from my work, you'll see that my work is mostly about applying the outcomes of brain research and of music cognition to the world of live performance, and something I continue to do through teaching. My students often get an opportunity to bring their research out onto the stage. We consider stage experiences to be absolutely critical validations of scholarly work in the lab. So it allows us to synthesize and sonify and get feedback on the successfulness of our work. So there's a little bit about what I do, and I look forward to receiving questions from you guys out in the ether about the kinds of projects that I continue to work on. So thank you for the opportunity.
Yeah, sure. Thanks, Teresa. So just a quick follow-up for you. I know that lately you've started to apply some of this measuring technology, these physiological leads, where you can measure things like heart rate and a galvanic skin response. You've started using that on audiences and not just on musicians and conductors, right? So are you able to start learning something about sort of the shared emotional or physiological experience of listening to music?
Thank you for the question. Yeah, in fact, a couple of years ago, I did a project with the Boston Symphony where we simultaneously measured the conductor and 32 audience members, and we were able to show a very high correlation, 0.86, R squared equals 0.86, across the conductor's heart rate and the audience's emotional intensity response. And it was a fascinating result. We validated over several pieces in the same concert. In other words, we got a similarly high value. And we're trying to figure out why. We have a lot of ideas. Of course, it seems like an intuitive result that, of course, audiences are moved by music, and that's perhaps one of the reasons that music exists in the first place. But there's very little experimental evidence to prove not only whether that is true, but why. What are the mechanisms? And this is the next phase for me, is to look at all the mechanisms of contagion and entrainment and some of the other cognitive mechanisms of emotional communication, I think remain somewhat mysterious and hard to measure in a live performance context.
Fascinating stuff. Thanks so much, Teresa. I'd like to introduce our third guest now, and we're lucky to have Robert Rowe here today. He's a professor of music and music education at NYU and also Associate Dean of Research and Doctoral Studies at NYU. And Robert, you finished in '91, if I'm not mistaken, and you were the first composer who completed the PhD in Music and Cognition at the Media Lab. Is that right?
Yes, that's correct. Yeah, so I left there in '91. Was one of the, actually, we just had the 30th birthday party of the Media Lab, and I started there 28 years ago. So I got there shortly after the doors opened. My committee was very similar to Teresa's. I worked with Todd Mackover also and Marvin Minsky quite a bit, and then my third member was John Harbison. So one of the world's great composers. But my own background is in music composition, so what I was working on and still work on are writing programs that are able to perform music, actually improvise music. So one of the things that my software does would be to improvise music with human players. So in order to do that, I wanted to learn more about human musicianship, human music cognition, because the more my feeling was, the more we understand about how people do it, the better able we might be to encode it in computer programs. So I did quite a bit of work on that. Still am doing work on it, and have there's a number of recordings out there documenting how that works. I actually did a concert for part of my PhD defense with Steve Coleman, improvising with software that I had written. So Steve is a fantastic improviser, actually writes a lot of software himself, but was one of the winners of the MacArthur Award last year. So subsequently did a number of projects in this area, one of them with Gottfried Schlag at Harvard Medical School. Beth Israel Deaconess is one of the leading practitioners of using fMRI to study brain responses to music, and we were looking at human emotional responses to music. So we played a number of different examples to human subjects, trying to map how features of the music changed their emotional responses to music while they were listening to it. And we were trying to do that with an eye towards possible therapeutic uses for music. We know that music has powerful therapeutic qualities. For example, there are studies showing that white blood cell counts go up faster in recovery rooms for patients who bring in music to listen to than for those who do not. So, asking the question, how can we get to the point of having doctors prescribe to patients, make sure you bring your iPod with you to the recovery room, because that's some of the best medicine we can give you. How can we establish that sufficiently that would be a common thing for a physician to say? So we did a lot of work with fMRI, but also with other kinds of studies to show the relationship between musical features and emotional responses, and being able to actually predict what the emotional responses would be to music, to examples that people hadn't heard before, so that you could ask for an exciting mix of R&B music. or calming mix of classical music. And got pretty good pretty good prediction rates. Particularly, it depends on how you characterize emotion. But one common way is to use a two-dimensional space of arousal versus valence. So arousal being calming versus exciting, and valence being negative versus positive. And you can do pretty well with arousal, I think, because it's largely physiological. So the biggest predictors for arousal are loudness and tempo. So as it gets faster and louder, it gets more exciting. I mean, that's almost no big revelation to say that, but you can make pretty good predictions about that dimension of emotional response based on those physiological markers. And then most recently, I've been working on a project looking at musical rhythm. So it was interesting what Mara was talking about in terms of prosody and how rhythm works in language. We're trying to figure out more about how rhythm works in music, in particular looking at music cross-culturally. So it's work that's been funded by the Abu Dhabi Institute. NYU has a campus in Abu Dhabi that's funding research across a number of disciplines. Ours was the first one to get a grant that wasn't what you might call the hard sciences. So that wasn't chemistry or biology, but was really looking at music from a cross-cultural and interdisciplinary standpoint. So we've had 2 workshops so far where we brought in people from 4 areas: musicology, music theory, computational modeling, perception and cognition, and neuroscience, to try to understand how musical rhythm works across cultures and how they might influence each other. So one of my co-PIs is Godfrey Toussaint, who's a computer scientist who has developed a model for measuring complexity and similarity across rhythmic patterns. So if you look around the Mediterranean, you can see all these musical cultures from the Middle East to Africa to flamenco to European music to music in the Balkans. And you can kind of track influences, particularly of rhythmic behavior, around that rhythm. So he has models that will predict how people would judge the similarity and complexity of music, of musical rhythms around that ring of societies. So one of the things we're interested in is how much that kind of understanding is innate and how much is culturally biased. So how much of rhythmic understanding are we born with, and how much of it is tuned by the particular musical culture that we're enculturated in, and then how much of that how is it possible that it precludes other types of rhythmic understanding, or is it still flexible? Is there a critical period for learning rhythmic understanding as there is for learning language? So those are some of the things that we're working on now.
John, you're the I'm sorry, Robert. You're the composer in the group today. I wanted to ask you kind of an off-the-wall question. The more you learn about the physiology or psychology of rhythm, or about how to program a computer to improvise alongside a human performer, I wonder whether that affects your own compositional style. Does it get harder to write original music, knowing as much as you do about sort of the inner workings of music from a software perspective or a physiological perspective?
No, I find it very stimulating, because as you learn more about it, you build it into the software, and you want to see how a person responds to listening to it, but also responds to playing with it. Some of the most educational experiences I've had has been, giving it to a musician, giving it to Steve Coleman or somebody, anybody, and having them play with software you've written, and then seeing what they pick up on and what, they miss entirely, what the software does well and where it misses the point totally. So for me, it's been actually the opposite. It's really spurred a new way of thinking about composition. And it's also spurred a new way of thinking about prior compositions. Bach knew all this stuff even if he wasn't going to articulate it in the same way that we might, or Beethoven. You can look at what they're doing as a way to elicit these kinds of responses in listeners. They may even have been able to say it explicitly. But there's another whole subfield of people writing software to do automated analysis to tease out these kinds of relationships in existing music.
Okay, terrific. Well, thanks all three of you for telling us a little bit about what you're up to these days, what kinds of questions are on your minds. I'm actually going to go straight into the audience questions, and one of them relates to a theme we've been talking about, the physiology of medicine and of music and how it may actually relate to different kinds of therapy for patients. We have Ernest in Carlisle, Massachusetts, asking. He says, "I have atrial fibrillation. Would meditating while listening to music help to control the rhythm of my heart?"
Who wants to take that one?
Yeah.
That sounds like a medical decision, perhaps, but certainly.
Right. We're not in the business of giving advice here, but we're we are talking about the relationship between heart rate and medicine, right? So and music. So.
Yeah, and actually, we found that you could do that. Again, I'm not a physician either, but actually, you can change heart rates by changing the tempo of the music that people listen to. So it doesn't change it very much, but you can affect pulse by changing tempo. So I would suspect that there is a possible effect there.
Teresa, do you have interventions in mind in any of your studies? Are you trying to figure out how you could reverse engineer some of this stuff and turn it into treatments?
I've seen references to entrainment between heart rate and tempo, so I think one thing to understand will be, I presume that a lower standing heart rate or sitting heart rate would be helpful, right, in this particular situation. So certainly calming, low arousal music, low intensity music with perhaps lower tempi and perhaps less complexity might be helpful, but this is all just a creative response, and certainly more research is needed. Perhaps you might also try wearing a heart rate monitor under various conditions and observe what that does to your pulse rate, to your heart rate, and start to develop a playlist for yourself that yields you the outcome that is most helpful to you.
Okay. Here's a question on a completely different track from Paul in St. Louis. Paul asks, is there any evidence that learning to play a musical instrument for the first time is beneficial for an older brain? He says, 8 years ago at age 63, I took up the piano. I continue to play and practice every day at home and play weekly at 2 Alzheimer's facilities for the residents. Is this activity likely to be beneficial for me, aside from the satisfaction I get from it?
I think absolutely. I think what we're seeing is that any sort of complex cognition task can be protective even to older adults, right? So learning a second language, so any one of these tasks that really engages all these executive control functions, right, in terms of decision making and hand-eye motor coordination, I think would really be beneficial. So I say absolutely. Well, and also the mere fact that he enjoys it is also going to be really beneficial to his quality of life.
I should add that, there's a lot of controversy about whether music learning really does affect growing brains. So there isn't really an established truth about whether it helps young people, although we all, on some level, believe that it does. So certainly if it does help young brains, it no doubt helps aging brains like mine as well.
Teresa,
I would recommend a book called Guitar Zero,
right,
by Gary Marcus, who's a brain scientist here at NYU, who learned the guitar at an advanced age, let's say older than supposedly you're supposed to be able to learn one, and he monitored the kinds of changes, what it took for him to learn how to play, and then reviews the literature about whether you can learn when you're older, what kinds of changes it introduces to your thinking and so forth. So it's a great book, and it's very fun to read too.
And
that's a clever title too.
And Gary is also an MIT alum, an alum of the Brain and Cognitive Sciences. He worked with Steve Pinker.
Excellent, keeping it all in the family.
Exactly.
Okay, so Teresa, I was just going to ask you quickly, you have this You're the Conductor app, right, where people can stand in front of a simulation of an orchestra and use the baton to speed up or slow down the performance. So you probably had time to watch how different people use that, and I was just curious, is there any difference between how quickly like an 8-year-old would take to that application versus an 80-year-old? And do they each kind of figure it out?
That's a great question.
Yep.
And yes, we do see big differences. Of course, kids immediately jump in with enthusiasm and flail around and have a lot of fun with it. And adults tend to assume that there's a right way and a wrong way to be musical, and will approach the system with greater trepidation and want to know how it works. I've even seen trained conductors who really can get frustrated with the system if it doesn't follow them exactly the way they wish it to. So that certainly there's a range of experiences, and I think it has a lot to do with the flexibility of your assumptions going into that experience. So, yeah.
Cool. Okay, we have a question from Herb in Newton, Massachusetts, who asks, do different types of music produce measurably different brain activity? So I'm sure people have tried this, right? They put somebody in an fMRI and they play jazz versus, heavy metal versus classical. Can you tell the difference when you're trying to read a brain scan?
Who wants to take that?
I don't know if we can tell difference by genre. You might be able to. We didn't look at that. We were looking at other features like timbral quality, rhythmic quality, loudness, tempo, those sorts of things. Not stylistically. I mean, we have lots of data. You might be able to go back and look at it to see if you could predict genre. I think it might be possible to do, just because I think that genres are often separable by those same kinds of features. So by harmonic activity, by rhythmic activity, by the same sorts of things that we were looking at. So to the extent that you could identify genres by those things, you could probably recognize by looking at brain activity which genre was being played.
I'd love to add to that answer, too. I think it's a great answer. And I'd also like to mention that Robert Knight at UC Berkeley has been doing a lot of really interesting stuff with subcortical intracranial electrode measurements, where effectively he's creating a spectrogram of what the person is listening to at any moment. So rather than thinking about which portions of the brain light up, you could actually do that analysis straight from the sound frequencies themselves, to the extent that you could use MIR, or music information retrieval techniques, to extract style from a spectrogram. If you're willing to allow the probes to be intracranial, then certainly we can extract all the features.
Oh, wait, Teresa, try and put that in a little more accessible prose, if you would. Are you saying that we can put a probe inside someone's brain and figure out what kind of music they're listening to, or even if they're thinking about music, and then reconstruct the actual music?
Yeah, this is the amazing result. You can actually reconstruct nearly perfectly the sound waveform itself direct from the neurons that receive those frequencies. Since the brain is set up to perceive frequencies along the sort of sound spectrum that individual neurons light up when they receive that frequency, then you can reconstruct the spectrogram from those probes directly, if you have enough probes and if they're deep enough.
That's mind-blowing. I have to say, it's kind of amazing.
The follow-up, which they're not quite finished with yet, is that if you have an experienced musician who audiates or listens to the music internally, they can reconstruct that partially currently. I think they're a couple of years away from being able to reconstruct a full spectrogram of what you're imagining.
Wow. Very cool.
How close are those probes to the ear? I mean, it would seem like it would be mostly coming right off the basilar membrane, right? Or is it? Right.
Yeah, they're pretty deep, and it's an intervention that's only used in someone who already has a sort of intracranial intervention for some other condition.
Okay. Before we get too far down that rabbit hole, that's fascinating stuff. I want to jump back to a question, and this is also from Ernest in Carlisle, Mass. And Mara, maybe you can answer this. It's been observed that people who stutter often lose their stutter when they sing. And that's a prosody question to some extent, right? Do we know the answer to that one?
I'm only mildly familiar with this work, but I think one suggestion is that you may be recruiting different neural circuits for speech that you would be using for singing, and so by singing in that case, you're tapping into a different set of processes, and so therefore you're not having that same difficulty. And I don't know to what extent that might be similar to cases where people who are aphasic, right? Meaning they have some difficulty in speech production. It's also been shown that there's some dissociability such that they can still sing, right? And if they are actually taught to kind of produce language in a very melodic way, then they can actually kind of overcome some of that aphasia. So maybe there's a similar thing happening there. Maybe Robert knows more about the actual neural connections there.
Well, I only know that Gottfried Schlag's lab at Harvard has done quite a lot of that work. So they actually are able, stroke victims also, they're able to retrain to speak through having them say, and then it becomes less sing-songy over time when they actually talk.
Right, melodic intonation therapy, MIT, confusingly.
So, related to this, I'm curious whether people have brought poetry into this mix, because poetry is sort of halfway between everyday spoken language and music in some ways. And as a very, very amateur poet, I'm just curious whether speaking, reading poetry aloud or thinking about poetry, whether that has been studied and whether there are similarities in the patterns we can detect in the brain or the way that poetry gets processed in the brain. Is it close to music, or is it something else entirely?
I'm trying to dig in here. I know that people have put participants in the scanner and had them listen to kind of a variety of things, and in fact have tried to kind of tap the spectrum. So, okay, so another MIT alum, her name's Ev Fedorenko. She works in the McGovern Brain Institute currently. She's been really interested in trying to understand whether there's overlapping neural circuitry for language and music. And so what she'll do is she'll have people in the scanner and they'll listen to kind of different types of stimuli that are more or less like language, more or less like music. But I can't recall. So they'll do things like, you'll hear full sentences or you'll hear Jabberwocky speech, right? So this is speech that has syntactic structure but without semantic structure, and then maybe words that are semantic without syntactic, and then kind of compare that to various musical stimuli. And I can't remember the details about whether they have looked at things like poetry, but it would seem to me that that would be kind of in between. We've done a little bit of work trying to look at what kind of value rhythmic and rhyming stimuli might be for early readers. So, why is it that all of our kids want to hear Dr. Seuss, right? What does it do for them as listeners? And one hypothesis that I have, kind of going back to what I was talking about at the outset about the role of rhythm and kind of directing our attention to things, that maybe listening to that helps kids with word retrieval and with understanding, and then also in contexts where they're reading, that can really help them decipher what the stress patterns of words might be, right? Because you set up a particular context where these words are going to appear on these stress syllables, and then that helps them a little bit better to do that access. But we're just at the beginning of that sort of project, so I don't have a lot to say about it.
Okay. A really great question just came in. It's sort of a nature versus nurture question, and maybe all three of you can tackle it. The question from David in Ottawa is, are great drummers born or made? In other words, are the brain structures that perform timing capable of resolving timing to the sub-millisecond level, apparently? Are they there from birth, or do the brains of percussive musicians get better at detecting fine temporal patterns?
I'll jump in without a lot of data to back me up and say that both, in the sense that having taught theory and musicianship for 10 years now, I can see that certain people just come into the world with better equipment, in the sense of better perceptual abilities, better timing, better sense of rhythm, and the better ability to perform a rhythm. So yes, that certain people, it seems to be have innate abilities, or abilities that they come into music training with. However, there is a huge range of variability in training, and I'll just say that, regardless of what kind of equipment you come to musical training with, everybody is capable of improvement. Whether it's 10% or 500%.
To bring a related question from Anne in the Netherlands, is perfect pitch explained by some special features of the brain of people with this capability, or is that something you can learn as well?
Perfect pitch, I understand, can be learned under the age of about 8. Does anyone else have have research to back that up?
I think it's fairly complicated. I think exposure to music is required at a very early age. So, and probably Robert knows more about this because I think Schlag has looked at, for example, differences in brain structures for people with perfect pitch versus not. But certainly, I think the earlier exposure, the better. And I think by the time you're age 4 or 5, if you don't already show perfect pitch, it's going to be really hard to show that. But then there's also really interesting work on acquisition of perfect pitch. So, for example, people who grow up learning a tone language. So, for example, Mandarin, right? Which in Mandarin, tone is lexical. So that means a particular syllable can indicate different words depending on how it's produced, so with a rising tone or a falling tone or a flat tone. And so there's some suggestion that people raised in a Mandarin speaking environment who also get musical training are much more likely to develop perfect pitch than people who were not raised in a tone language environment. So suggesting that there's some interactions of nature and nurture in those cases, right?
And I would agree with both of you, but to echo what Teresa said, that it's both things, nature and nurture, in terms of rhythmic production in particular. In one of the workshops that we had, we invited Dafnis Prieto, who's a Cuban drummer, and I think everybody is born being able to differentiate rhythmic differences down to the millisecond level. That's innate. But somebody like that, when he gave his talk, he was producing the clavecin through the entire talk. So he was basically clapping like this while he was talking, which I can do maybe once or twice, but for him, he's done it so often it becomes automatic. So the automaticity is what's different between somebody like that and the rest of us, is that he's internalized these rhythms to the extent that he can produce them without thinking about them. So that's the difference between him and us.
That's great stuff. I'm going to try one more question here before we're out of time, and I guess it's about the difference between the lyrical content of music and the musical content of music. So Gary in Denver says, I frequently noted significant emotional responses to operatic arias sung in languages I don't even understand. Is there something about the voice rather than lyric, right, that promotes responses? And so I guess, to extend that question, is there anybody studying, could you, for example, put nonsensical or actually, antithetical words to the same tune and get the same emotional response? Do you try and mix these things up?
I can't speak to the research necessarily, but I can speak from the creative side that certainly, in the same case as instrumental music without words, or music with words that lack meaning, that there you're looking at all sorts of parameters, musical parameters, from pitch, height, and delta to the timbral quality of the voice as it takes on greater tension. The vocal cords under tension produce a different timbre, and so you may be reacting to all sorts of simultaneous parameters indicating tension and release over the course of a phrase that would give you some guidance about what the emotional contour that the artist is trying to portray.
And usually they are trying to be complementary, so it's hard to tease out which part is coming from the lyrics and which is coming from the musical qualities. But I asked my students once as an assignment to try to find a song where there was the strongest mismatch possible between what the lyrics were saying and what the music was saying. And my favorite was a song by the Smiths called Girlfriend in a Coma.
Perfect.
Very disturbing lyrical quality, but it's really soothing.
That's a really happy song. I mean, when you discount the lyrics.
So, Robert, we had a request come in that you play the keyboard, and we can tell you have a keyboard there in your office, which I think means that next time we do this, we're going to actually have to have a concert instead of just a conversation. Thank you. Obviously, yeah, we could we could go all afternoon, and this is just such interesting stuff. So I really want to thank all three of you for taking the time to join us today. So Robert Rowe from NYU, Teresa Nakra from the College of New Jersey, and Breen from Mount Holyoke College. Thank you so much for joining us. On behalf of the MIT Alumni Association and the STS program here at MIT, I'd like to thank you for tuning in today to this Faculty Forum Online Alumni Edition. We did not get to all of your questions, but we'll share the rest of the questions with our panelists by email, and they can follow up at their leisure. And a special thanks again to all of our listeners, and you can send feedback about this program or other programs in this series to alumnilearn@mit.edu. And you can tweet, again, using the hashtag MITalum. So keep an eye on the alumni website for future Faculty Forum Online segments, and we'll see you again, if not this year, then in 2016. So thanks again, everybody. Take care.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.